Good evening, everyone. Today we start a course in neural networks that will contain 4 lectures, and during these 4 lectures I expect to guide you through all basic details of the neural networks, starting with what they actually are, how do we need to think about neural networks, and ending with starting certain neural networks and different devices, including some embedded devices. So here is the lecture number 1, and let's begin. First of all, what is neural network? We can tackle this problem from basically 2 different sides. One side, we can think of neural networks like engineers, and the other side, we can think about them like mathematicians. So as engineers, we can consider a neural network, well, as basically any machine learning algorithm, as some sort of program. So that's a certain type of program that contains so-called trainable parameters. So we have certain parameters that are set inside of this model, and then we use this model to predict something or to do something useful for us. The difference between classical, so-called classical programs that we are used to and machine learning program is the existence of training algorithm that calculates for you these parameters. So I really like the example when I'm showing difference between let's say some standard program and machine learning approach using this kind of problem. So suppose you are creating a program that is answering the question whether you can have driver license. So you want to obtain driver's license, and you need to write some programs that will tell you can or you cannot. Consider a very simple case. So suppose you can get driver license depending on whether you have a certain age. So if you are 18 years or older, you can get that license. So in classical approach, you will write something pretty similar, pretty simple, something like this. So if, let's say, user point age is greater than 18, you return true. So you can have driver's license. Else, you say no. This is a pretty classical approach, so a pretty classical program that we can write and that will work. What is the difference with this program and machine learning approach? Here you have encoded some sort of parameter that defines how your program works, and this parameter is hard-coded into your code. Now I want something pretty different. I want to get this parameter basing on some data from the outside world. So suppose I have some sort of database. So here is my database that contains different people that have obtained driver's license. So I don't know, some John he's 40 years old and he has driver's license. For example, I don't know, so Mary has driver's license and she's 19, and so on and so forth. So many people. With ML approach, I can take this database, I can find some minimal age, and I will get some number that may be 18. This number I will set into the program that defines whether you can obtain that license or not. So basically the same program, but I leave here like placeholder. So user age greater or equal, let's say some parameter a, and here I return true, else false. And this parameter a is set from here. So finding this minimal age is some sort of training algorithm that considers some data from the outside world, computes some parameter, in this case it is a minimal age from the database, and sets it into the program. Now I can use this program and immediately get some results. Of course, this approach may look for you a little bit redundant. So I have created, instead of one program, I have created two programs. So now what's the point? Why do I want these two programs instead of one program? Well, the thing is that creating these two programs, I get certain benefits. First of all, this program, it's hard-coded. If I want to change something, for example, in one state you can get driver's license when you are 18 or older, and in some another state you can get that if you are 14 years or older. And in some different state you can get that if you are 16 years or older, and so on. So these parameters may vary depending on the state. So if you want this program to be used in a different state, you will need to change the code, you will need to recompile the program, so on and so forth. In this case, I am using data. So this program does, you don't need to recompile this program. You need just restart training program and get your parameter that will be used here. So you are just getting database for the state that you are interested in. You run your program, you get minimal age, and you use that number in here. So you don't need to recompile anything, you just need to restart. So that's a pretty engineering approach. And I will show you different examples of machine learning algorithms and what do we do with them and what they can do for us. And basically you will see this once again and again and again. So this is the basic idea from the engineering point of view. You are creating some program, it has some free parameters inside, and you have a separate training algorithm that defines these parameters for you, basing on certain data from the external world. So that's what we have. The other view is the view of a mathematician. So for the mathematician, neural network is just a function. It may be really, really complicated, but that's just a function. And what you want to do, you have some idea of some perfect function that performs exactly what you want. So you give it some data and you get exactly the result that you want. And training process is basically searching for this perfect function. Of course, you cannot search in the whole space of all possible functions. The space is too large. But you can create some models. So you take some families of functions. These functions are basically indexed by certain parameters that correspond to that parameters in engineering point of view. And you are wandering around this space, searching for the function that matches the best to your target function. So now let's consider the mathematician's point of view a little bit more carefully. So here you see in this slide, you see the space of all the possible functions. So these are all functions in the world that may exist. And here you see our hypothesis set. So this is the set of the functions that we may consider. So this is the family of the models that we can consider. And within these functions, we are searching for the function h that is the closest one to the function f that will be a perfect function for our problem. Of course, at this point, you may be having some questions regarding how do we consider these functions and these models so simultaneously. Because we all know that neural networks is probably something that, I don't know, takes a picture and recognizes that you have a cat in this picture, or counts something, or answers your questions, and so on and so forth. So what does it have to do with all these functions and all that abstract things? So let me show you that we can reformulate all our problems, all the problems that are solved with neural networks, in the framework of functions and searching for that best function. And that's what we do. consider we have an image as an input. So image is, you can think of it as a matrix n times m that contains certain numbers. Each number corresponds to a pixel and tells you, let's say, a brightness of that pixel. If I take all these numbers and write them in a line, I get a long line, and these all numbers, they are written in a row. I can basically consider these as an element of certain highly multidimensional space. So it has dimensions m times n. So I had the number of pixels in the image, m times n, and here's what I have. And there may be some function f that does something to this vector, creates a new vector with dimensions m times n, and I can once again rearrange this number in this sort of matrix, in this sort of picture, and reinterpret them as pixels, so as the brightness of the pixels that I have in the picture, and as a result I will get a new picture. So basically this function takes one picture as an input and gives you another picture as an output. And that may be basically anything. So for example, you are using Zoom for some sort of internet conference, and you don't want anyone to see the background, and you have some neural network inside that takes a picture, a frame of you sitting somewhere in the room, and creates another picture where you still are sitting, but instead of the room there is something different on the background. I don't know, something different. Good. Another example that I want to show you, it's not, let's say, obligatory to create picture from a picture. You can create something pretty different. Here we have an image as an input. Once again, I can transform that image into a vector from the space R with dimensions m times n, and I have a function, but this time this function does not return you a vector r from Rm times n. It returns you some different vector from the space with k dimensions. And this vector may have a pretty different meaning. For example, you can reinterpret numbers in this vector. You can take them by 3, so three numbers, and consider them as a point in a 3D space. And so you have a few points in a 3D space, and you can reinterpret them as positions of joints from the hand. So we have a hand, we are showing an image of a hand to a neural network. It transforms that into some positions in 3D space that correspond to joints. So I want to show you a small demo right now. And before it starts, I can show you an image from the lecture in ITP that we were where we were testing this sort of demo, and you see the hand that was recognized during that lecture. Okay, so let's try to start this demo locally. So here we have some code. I'm starting this code, and you see that and now you see that we are getting some image from camera, and if I show a hand, you see that neural network detects this hand, detects fingers, and transforms basically an image into positions of the joints. So let me write this way. So we had an image, and this image is transformed into a vector in a multi-dimensional space. So all these pixels, they have some brightness. This brightness is used as a number in here, so I'm setting these pixels in here. And I have a neural network that is basically a function transforming that into a new vector. And now I use triples of these numbers. So these sort of triples, and reinterpret them as a position in a 3D space. So this triple describes me a point here, and the next triple will describe me point somewhere here, and so on and so forth. So this is a long vector, and if I draw all these points, I will get some sort of a hand in a 3D space, so some fingers and so on and so forth. So you get the idea. The same interpretation may be applied in many different cases. I will show just few of them and we will continue. So here's another case. Here we have two different functions, like two different neural networks working on one image. So one of these networks is getting a face from the image. You can get some sort of positions. So basically we have, once again, we have an image transformed into a large vector, and this function gives you another vector that contains 5 numbers, and these 5 numbers are coordinates of the upper left and lower right corners of certain rectangle. That rectangle should cover a face in this image, and a number that tells you the probability that whatever is in this rectangle is a face. That may help you to cut out a face from the image and to use that face, maybe rescale it somehow, maybe do something different, and do that and use that face for processing. And here is another way of processing. So here is a function f prime that takes once again an image, but now we know that this is an image of a face. Well, maybe it is scaled to certain predefined sizes. So I have once again large vector of m prime times n prime, and this function transforms that into some pretty abstract vector of a pretty, let's say, arbitrary dimension that describes this face. So this is a problem of an embedding. So from a photo I can get someone's face, and I can transform that face into a vector, into an abstract vector that describes this face. Why do I need that? I want such a function f prime that will give vectors for one person pretty close, while for different persons these vectors should be almost perpendicular. So I can use these vectors to check whether the person I see in the image is the one I'm thinking of. So maybe I can use that for recognition of people and something like that. So here is another example from the lecture at ITP that we have tried a demo that is recognizing people, and I will try once again to run a demo right here, and we'll check what happens. So here I have started the demo, and you can see that in the console we have these sort of numbers. That's basically I have used one of my photos to generate these numbers, and these numbers, they describe my face. So whenever the model sees me, I can get some sort of numbers. I can compare them to these numbers by basically scalar multiplying vectors that I have, and this defines my face, and it can recognize me right now in this photo. Okay, let's try doing that for two people.
Hello.
So now you can see that model can distinguish between us, and even if we try to somehow mix with the model, so let's say I will go somewhere in here, that still recognizes who we are. So I can cover the camera for a moment and uncover the camera, and you see that model works, well, more or less. So in each frame it is able to recognize us and give some sort of labels to who we are and what do we and what we are and who we are. Good. Now let's move further. So here is example from the previous lecture that we have. Here we have detected more people. So good. At this point, what do we have? So we have defined a neural network as some sort of function, and we have defined our training procedure as the procedure of finding the best function that matches our needs. So now we have few questions at hand that we should answer. So first of all, how do we choose that family of the functions? And we know that these family of functions, it should be parameterized with a finite set of real numbers. That if you take some sort of very large family that is not parameterized with the final set of real numbers, you just cannot fit that into computer. So you need to restrict yourself. The second thing, if we have I take some function from that family. Okay, how do I know that this function is good or it is not good? So how do we measure the goodness of the function? And of course, if we measure that goodness somehow, we should think how do we maximize that. So I have a family of functions and I cannot do something simultaneously with all that functions in the family. So I take one of them, I consider that function, I see it is not very good or pretty good, and now I want to change something. So I want to take another function that is better than this one. So how do I do that? And there are certain number of methods that we will consider. So we need some sort of iterative process that will converge and give us the best function. Okay. Now getting a little bit closer to neural networks. So we know that neural networks, they started as some sort of analogy with real life neurons. So here is an example of a real life neuron. It has some cell body, it has dendrites. These dendrites, they are taking some sort of impulses from the outside world or from other neurons, and they are getting some sort of information. And at some point, this neuron may consider firing sort of action potential, and that action potential will propagate through his axon, and then maybe stimulate some different neurons, and so on. And this was modeled, first of all, with this type of simple neuron. So this is our artificial neuron. It has a certain number of inputs that mimic dendrites. Each of these inputs has some level of a signal. These signals are weighted with some weights and summed up, and if this sum is higher than certain threshold, we consider that this neuron should fire an action potential. This consideration is performed with this sort of function that is called activation function, and this activation function acts on this sort of weighted sum of the inputs and maybe some bias added. So this b is some constant, some bias, and these are different parameters. What are the activation functions? So here you see a number of different activation functions, a sigmoid function, a tangent function, ReLU, so on and so forth. Today, I guess the most used is the ReLU function. It's most cases I see these function in different layers in neural networks. Regarding layers, so we have considered one neuron. So we have a neuron that takes some inputs and that generates you some output. Now, how do we connect all these neurons? So we have certain neurons that are getting input from the outside. For example, these are the neurons that are getting data from the image, so that brightnesses of the pixels. And we have some neurons that are generating something for us, that resulting vector that we want to get. So these are input, this is an input layer and this is an output layer. And we may have some neurons inside that are performing some work, and we call them hidden layers. Regarding layers, the thing is that whenever we consider something and we have some small details of that something, we can construct from that details, we can connect them in different ways. And the thing is that at some point these small details, we get so many of them that we cannot handle that in our head. So what do we do in these cases? All the time we do the same thing. We collect them in some larger blocks, and then we forget about small details and we consider these larger blocks. In case of neural networks, these larger blocks are layers. So I connect neurons a certain way, I create from them some larger block called layer, and then I operate with that layers. So here you see 3 layers, and now we will consider a little bit in depth what can be different layers, how do we differently connect that neurons, and all that fancy names of the layers. So here is example number 1. It is called a fully connected layer. This means that all the input neurons are connected to all neurons of that layer. So fully connected layer takes all the inputs that are that we have at some point, and then it takes all that inputs to all the neurons in that layer. Convolution layer. A little bit more complicated. This layer was especially designed to work with images. We know that pixels in image, they have some additional, let's say, information in their position, because pixels that are closely together, they probably represent colors of the same object or something like that. So there is some additional geometrical information that we have in that pixels. And this sort of convolution operation that we are performing is trying to retain that information by operating with that pixels that are neighboring in the same way. So here is an example shown for you. We have an input image, we have a kernel of that operation. Most cases you will meet layers with 3 by 3 kernels, but of course there may be some different shapes and sizes. And what it does, it takes each of these pixels, it multiplies that by a coefficient in the kernel, adds everything together, and puts into the destination pixel. So I will just briefly draw on a blackboard. I know this operation may be a little bit confusing. So here I have an input, some input image. That may be the input image you get from camera, but that may be a result of processing in the previous layers of the neural network. So that's what we have. Now what we do, we have some output, maybe same size, maybe smaller, that depends, and I take all the pixels, let's say in this area, so these 3 by 3 block, I multiply each of them by certain coefficient, and I add everything together. I can write that in a more mathematical notation. So if I have some central pixel with coordinates ik, and I have a kernel, let's say with coefficients w, alpha, and beta. So here is my kernel 3 by 3. I use that to perform convolution, and I say that my alpha and beta, they are from, I don't know, -1, 0, +1. So I should sum by alpha beta from pixel I plus alpha j plus beta times w alpha beta. So I sum everything up and I get a new resulting picture, so a new pixel in this image, let's say j, with coordinates I, j. So I place result of that operation, let's say in here. And so I move this kernel to the next patch. I take all the pixels, multiply by weights, add them together and put in here, then in here, and so on and so forth. So this way I go through all the image and get some, all the input image and get some output image. So here is example of the convolution layer. This convolution layer is pretty similar to what we have in our eyes. So this is just an example that we have photoreceptors, and these photoreceptors, they are basically calculating some difference between central receptive field and receptive field surround. And this is pretty interesting difference. This is pretty interesting effect, because it's not only shows some sort of connection between our convolutional layer and some sort of biological processes, but it has certain influences, like for example this image that you see. Since we are considering only differences between neighboring points, we see in this image something like two colors. So some gray color on the above and some white color from the below. But if I go here and let me hide this part, you can immediately see that colors above and below are basically the same. So here I show it, here I hide it. One more layer often used, here you see so-called max pooling layer. So max pooling layer, you are taking your input image, you are splitting that into parts, and from each of that parts you are taking the maximal number that you have in that part, and from that maximal number you are constructing a new image. These layers are often used when you need to make the size smaller. Most cases that is used to make the image twice smaller than it was before. So here is an example for you where you have these sort of input and you are splitting that input, and here you have your output. This input, you might guess that it came from some previous layers that we have had in the neural network, because here we have some negative numbers and so on. So probably it was generated from some previous layers, but anyway we use on that max pooling layer and we get some smaller result. Here is a recursive layer, so you may have layers that contain certain internal parameters, and these internal parameters may change during training or operation. So here is a so-called recurrent layer. It has internal parameter v, so when you are putting some input, some x as your input into this layer, it gets some sort of additional input. So this input is augmented with some parameters v, and this layer performs whatever it performs, but as the result you get some output w. So you show this output to the user, you pass that to some next layers or whatever you do, and you get your internal parameters updated that should be stored somewhere, and then you use that on the next input. These layers we will see later when we consider some sort of recurrent neural networks and how do we work with them. So here is example of the batch normalization layer. This is a normalization that is performed basing on the on the batches. So when you are passing a number of different inputs, and these different inputs they may contain some sort of variation or some sort of outliers and so on. So in many cases you want to perform some sort of normalization of inside your network, or even at the input of your network to get, let's say, better results. Here is one more example. That's a dropout layer. This layer is interesting because you use that during training to shut down certain neurons and to force other neurons to learn. So it may happen that when you are training your neural network, only a part of your neurons is basically training, while the others are generating some sort of noise or at least nothing useful. So with dropout layers, people try to force all the neurons perform something useful, and this layer is operating during training when you are just turning off a part of your neurons. And here is an example of using that layers to create maybe the simplest neural network called LeNet. So that was probably the first network that performs something interesting like recognition of different digits, and you may find on the YouTube some videos from the 98 or something so year, and you can see the first run of the LeNet on computers from that era. So here you see different layers. These yellow are convolutional layers, red are max pooling layers. We have considered all of them, and here you see like when information is passing through these layers, the shape of the layers is changing. You see that one layer may have different channels. That means that you are performing the same convolution operation, but you get you can perform that with few different kernels and then stack your results together, and you say that these are channels, so channels that you get from the convolution. And here green, these are fully connected layers, and the last output layer, it's as well fully connected, but a function softmax is applied to get number from 0 to 1, and that defines you the probability that you get a certain digit. So these are 10 numbers, and each of them tells you that there is a probability 1% this is 0, 5% this is 1, and I don't know, 80% that this is 2 or something like that. So here we have it. And here are certain neural networks and their architectures. We will consider that in a bit more details in the next lecture, but what I want to show you that first of all, network may have many parameters, so starting with 60,000 in LeNet, and here we have like hundreds of millions in VGG, and even modern networks like ChatGPT. I don't know, there's some enormous number of parameters, like some billions or something like that, so some incredible numbers. So here we have these sort of so we can combine all the sorts of layers into some final architecture. So what do we get with that? Basically, combining layers into an architecture, we get neural network, and with that architecture we define a family of functions that we are working with. The numbers in that layers, like numbers in the kernel of the convolutional operation and so on, they are basically defining a concrete exact function that we are considering at this point. And the process of training is basically finding the best parameters for all the layers that the neural network performs exactly what we want, and not something different. So basically, making a neural network, we will try to follow that path. So we will create different layers, we will connect them somehow, and then we will start a training procedure that makes these that finds the best parameters. We will mostly work with with the PyTorch. I guess this framework is quite used today, and I guess it's the best case scenario is consider exactly PyTorch and its capabilities. Here we have different layers that we can use in the PyTorch, and here you see how these layers are created in the PyTorch. So here is some sort of code, like if you want fully connected, you create an linear and you say how many input channels and output channels you have, and so on. I guess we will consider that in a bit more details in this, even in this lecture. Okay, so where are we now? So we know that we are searching for a best function from certain family of functions. We know that a family of functions is defined as a neural network architecture. We write that by hand, or maybe we have certain ideas, but anyway, we create that. Then we need to find from that family of functions the best function. That's basically corresponds to finding the best parameters of our neural network. To find that parameters, first of all, we need to know how do we define what is good, what is not good. And here are a few examples for you, because this definition should be performed by people as well. So we need to say what we consider solves our problem and what we consider does not solve our problem. Here are a few examples for you. First one, intersection over union. Suppose you are considering some problem like finding a bird in an image, and this bird you give an image to the neural network produces for you something that defines where the bird is. It may produce you a rectangle, and the bird must be inside of that rectangle, or it may produce for you some sort of mask, like telling that this pixel corresponds to a bird and some different pixel does not correspond to a bird. How do you define what is good or not in this case? So here is a metric for you, so we can consider some sort of ground truth. Maybe we have drawn that rectangles by hand and we know that the bird is exactly here. Or maybe we have some sort of masks painted, so we took, I don't know, paint or some different editor, and we have put certain pixels, and we told that this pixel belongs to the bird and this pixel does not belong to the bird, and so on. But anyway, we have some ground truths, and we now can compare whatever our neural networks gives us to the ground truth that we have. And we may calculate the area of that is intersected, so where both our ground truth and our neural network consider that pixels belong to the bird, and we can consider area that is not intersected. So the pixels that are either considered as a bird with our ground truth but not considered as a bird with our neural network, or pixels considered with neural network as a bird but not considered so by our ground truth. Taking all these pixels together, we may find these sort of parameters like intersection, so pixels that are both considered by them as a bird, divided by union. So these are all possible pixels. So pixels that are considered as a bird by either ground truth or our neural network. You may see that in a perfect case, intersection and union should coincide and you get 1. In case if this number is smaller, for example, it guesses the bird somewhere off and there is no bird, you get 0. So this is a nice number from 0 to 1, where 1 is the best case scenario and your neural network works perfectly, and 0 is basically the worst scenario and your neural network does not work. Here is another example. You may have a problem of so-called multi-class classification. So I give an image to neural network and I get, let's say, what is the object on that image. So there may be many different classes of objects, so a person, a bird, a dog, I don't know, a table, a computer, whatever, so many different classes. And of course, in some cases, your neural network will tell you exactly what is there, and in some cases it will make some sort of mistakes and give you some wrong information what's in that picture. And how do we consider that? In case of multi-class classification, we can consider so-called true positives, false positives. So for each class we can calculate how many times our neural network told us the correct result, how many times it didn't tell us the correct result. Here you see two nice parameters to consider. Precision, that's basically from all the elements, there are certain elements that were selected with neural network and that was classified as certain class, let's say as a person. And some of them are okay, some of them are not okay. So here in the precision we divide the number of pictures that were correctly classified as a person by the all pictures that were classified as a person. So this number of course is from 0 to 1, so depending on the situation. And the other parameter is recall, that is basically the number of all correctly classified images as a person divided by all images that contained a person in the dataset. So how many of that picture of the pictures of persons were of people were selected from the dataset. Once again, you get a number from 0 to 1, and they tell us how good is our neural network at classifying a certain class. If we have many classes, we can consider this sort of score, F score. Here you have precision times recall divided by precision plus recall, and you get some F measure that tells you how good is your neural network with certain classification problem. Here is another problem. You may have so-called regression problem. So you give some data to your neural network, and it gives you some sort of real number. And how do we know that this real number is good? You can calculate these sort of measures for the regression problem. So the simplest regression problem is something like drawing a line through the points. So you have a point cloud and you are trying to draw a line through that point cloud that and basically can be reinterpreted as the approximation of the measurement. So that points are some sort of measurements that you get from a device, for example, and you are drawing a line that should describe how that device describes some sort of theory, and here is an example of a linear theory and some sort of measurements that are pretty off the line. But anyway, you can make your decision on the parameters of this line, and then you can calculate these sort of numbers like r squared. That is the fraction of explained variance, and this explained variance tells you how good is your model performing some regression problem. Here is another quite non-trivial case of estimating how good is your neural network. That's the case of autoencoder. So autoencoder takes some image as an input and then processes, and as the result it gives you the same image, and basically your estimation whether it's good or not is based on the fact whether it returns you the same image that you had at the beginning or it made something different. So that's what you have. You may of course ask, why do we need a neural network in here? Because we are just making from the input the same input. And if you look at the architecture of this network, you see that layers are basically shrinking. So you are making from a large picture, you are making some smaller and smaller pictures. So it looks like something like this. So I have some large input, but then it is processed and made smaller, and then even smaller, and then I'm making it back larger and even larger. And the thing is, if I am able to make this picture the same as this one, this means that information passing through this small layer, well, we have retained all the essential information even in this small layer. So information in this layer was enough to reconstruct a large image. So that's what we have, and that may be really crucial in some cases when we need to make some smaller dimension from the large image or something like that. So that's really interesting architecture, and I guess we will consider it a little bit later separately. Good. So what do we have now? So now we have a family of functions. So we have created some sort of neural network architecture. We know about layers. We have taken these layers in certain order. We have that sort of architecture. And we know how do we assess how good is our neural network. So we can get some number that characterizes to us whether it works okay or not okay. Now we need some process that will make our network iteratively better. So we need to find the best possible function in that family of functions, or let's say that more engineeringly, we need to find the best set of parameters for our neural network so that it solves the problem that we want. How do we do that? We use optimization methods. So here is a small image that shows you that these optimization methods, they can be, for example, different order, like 0 order, first order, and second order. In training neural networks, almost exclusively first order methods are used. Second order methods, you can't probably fit them into a memory of the computer, because neural networks have quite a lot of parameters, and second order methods, they require you to consider like an n squared of the parameters that you have. So they are order of the memory used is n squared, and that's a bit too much for the sizes and number of parameters expected for neural networks. 0 order probably can be used, but I have never seen that, and first order are used all the way. Here are examples of these first order parameters, starting from a standard gradient descent discovered 1847. So it has been with us for a while, and here we have some different modifications. The first modification was adding momentum. It's 1964, and here we have much more and more different modified methods. So of course, they have mostly appeared, as you see, in 2000s, because that's the moment when we started to extensively use neural networks for something, train them, and they became, let's say, once more popular. So it shouldn't be strange for you that that are basically the years where these methods appear. I will not get into the details of these methods, but I will just show you how do they look like in a pretty simplified case. Here is a very simplified case, a function in the 3D, and how these methods are trying to find some sort of minimum when we start at some point. So here you can see how these methods are performed iteratively, and what are the next point for each of these methods that they propose as the better solution, as the better minimum for the function f. What does it have to do with neural networks and so on? Well, in case of neural network, we will have this sort of function like neural network connected to the function that estimates how good this neural network is. So we have already considered that we are trying to describe the goodness of neural network in terms of numbers. So we have some function that takes the output of the neural network and gives you some number that defines how good it is. Most cases, these functions are engineered so that they give larger values to the when your neural network performs more poorly. So the better your neural network performs, the lower is the value of that function. That's why it's called cost function. So that's the cost function, and you want to minimize, or it is often called loss function. So that loss function is the function that you want to minimize. So here is basically the overall scheme. So I have some sort of input. It goes into the neural network, goes into the loss function, and here you have some number, some real number r, and all these things, and you are trying to minimize the result of this loss function. So you are trying to minimize that by changing parameters of the neural network. So neural network contains many different parameters. So here you have some parameters, and by changing these parameters you are trying to obtain minimal value here. So let me better draw it so. So that's what we are trying to do. And this example, you can think of it like you have a neural network with two parameters. Yes, quite poor neural network, just two parameters, nothing more. But you have these two parameters. You have your loss function that, based on which parameters you have chosen and maybe your data set, maybe you have some sort of ground truth, whatever you have, calculates a number, a real number for you that tells you whether your neural network is good or bad. So the lower the value, the better is your neural network, because it's loss function. So you are losing something when you get some large numbers. And these methods, so listed here, they are basically some iterative methods that are trying to find you these points, so this minimum. And here you see how do they behave. You might guess that they behave, first of all, pretty differently. The second problem, they may get stuck in a local minimum. That's because you cannot assess the whole function. That's too complicated. If you have 1 million parameters in your neural network, just to take 10 points along each of the parameters to get some sort of tabular values, you will need 10 to the 1 million number of points. That's too much. You can never calculate that. So whatever you can do is just consider something locally in this exact point, and then make a choice whether you move to the next point or what exactly you do. You use these methods to minimize that function. How that performs exactly? So here is an example for you of a neural network. This is a pretty random neural network. I really doubt that anyone will ever construct something like this, because it doesn't do anything useful. But this is an example what happens in neural network during the training. So how do we use that method to perform training? So here I am having certain layers. So you see 3 layers here. Here I have some inputs, and in each layer I am calculating something. So basically I have some neurons in there that calculate some values. Here I use some pretty random functions like sines and cosines. In practice that will be something like weighting inputs and calculating ReLU or something like that, but it doesn't really matter. And in each layer I can calculate derivatives. I can calculate derivatives of these functions, so they are known, they are analytical, and I can find them whenever I have parameters. What do I do first of all? I initialize the parameters. That corresponds to finding some random function of that family of functions, so I'm choosing just at random. That's the best I can do when I just start this problem. Then the so-called forward propagation. I get some inputs, I calculate these functions, and I calculate the values of the partial derivatives. So here you see how this process propagates, so that's why it's forward propagation, and here I have all the results, and I get some loss function that estimates for me how good is this result. Now I show you so-called back propagation. So I have calculated this forward, and I get some result from my loss function, so I know how bad is the situation. Now I want to make my parameters of the neural network a little bit better, for example using that sort of gradient step. To make that gradient step I need to calculate the gradient of the overall neural network, and that seems to be possible. That's pretty possible. So let's look how that's performed. So let's start, it's called backward propagation. Why backward? Because we start at the output. So let's look at the output, and you immediately see, so if I write a gradient of all the neural network, It looks pretty awful, but here these two slots at the end, they perfectly correspond to partial derivatives of the function f from the last layer with respect to its parameters. And I have already calculated them. So on the previous step, when I perform forward propagation, I get to that layer and I calculate these derivatives. So I have them. I can plug them in. No problem, they are plugged in. Okay, but what do I do further? You see that I don't have derivatives of the of other components. But it turns out not a big problem. I can take the derivatives I had in the last layer with respect to the inputs to that layer. So in the layer I have it's like a function that performs something. It performs something basing on the input values and internal parameters that it has. If this function is good enough, I can find derivatives with respect to all the inputs and with respect to all the internal parameters. I have just used all the internal parameters to set them into the general gradient. That was done. Now I use partial derivatives with respect to inputs, and I pass the values of these derivatives to the appropriate previous layers. So here you see how it performs. So I have these numbers and I pass them to the previous layer. Now what's happening there? I can multiply them with the partial derivatives that I have in that previous layer. I do that for everything I have there. So here you see how this information was passed, and now you see that this result of this multiplication coincides with whatever I need in my gradient. And it turns out that this is the problem of just multiplying two real numbers. So I have multiplied them and I have these sort of results, so I can plug them in. Now what I do? Once again, I use partial derivatives with respect to the inputs and I redistribute them to the previous layers and previous neurons that I had in this neural network. So here you see how that's done. They are redistributed and I perform multiplication there, and once again I get a result that can be plugged in, and this way I get the overall gradient, and this gradient may be used for a gradient descent step. Here is a simplified picture for you how that performed. So here is a neuron. This neuron gets some inputs and generates an output for you. When we do a forward propagation, I just get this x, y, and I generate v. If I have backward step, I get gradient that comes from the output. So there is some different neuron in that output, and it will generate this gradient for me and send me a number, its value. And I use this number to calculate all the local gradients I need, and something I use for the gradient step, something I send to the previous neurons that I had. So here you see that. So dl over dx is basically dl over dz, dz over dx. So here are these functions. And at branches, we just add gradients. So you can check that with the linearity of the derivative, and you have seen that in this sort of example. So here you see just addition of these derivatives, and if you check the math, you can see that really if you calculate all the partial derivatives and write them down, you will see these sort of plus signs. So it's really the case that you need to add them. So maybe looks a bit convoluted, but of course, but it's doable. So it's definitely doable. Good. So now we have considered all the basic theory that I wanted, and I guess we need to get a little bit into the practice and try to create some very simple neural network basing on whatever we know. Just a small recap. So what did we learn today? So neural networks are composed of layers that contain neurons. So neurons were first thought as some sort of mimicking some real-life neurons. Whatever we have is pretty different from a real-life neuron, but anyway, that works, so that's good. We know that this corresponds to finding some sort of function that performs whatever we need. We have seen like different problems may be reformulated in terms of function that maps from a some higher dimensional space to another higher dimensional space. So a space of all images may be considered as a higher dimensional space where each pixel corresponds to a coordinate, and we can map that image to let's say positions of joints of a hand. So that's pretty doable. That's pretty okay. And we know that we can estimate how good is our neural network by connecting that neural network to a function, to a loss function that takes result of that neural network and somehow estimates how good is that result, giving us a number. The higher is this number, let's say another way, the lower is this number, the better its neural network. So and now we have seen the method of using some gradient approaches like first order methods like gradient descent to tamper with the parameters inside the neural network that basically define which exactly function of the family of functions we are using right now to get the best result basing on that loss function. So now let's look at this part from the engineering point of view. So first, let's solve a problem of recognizing a digit. So probably the simplest problem that can be solved with neural networks. Let's recognize a digit. First of all, we need a data set. So we will solve this problem by creating some simple neural network. As a loss function, we will use a function that will basically check whether our prediction corresponds to certain ground truth, and to make that sort of check we need some sort of data set that contains images and some results that we expect to have. So here is this data set. So we have some small images like 8 by 8, and we have these images already recognized, so we can check that our neural network works correctly and prescribe some number how correctly it works. And here is our neural network. So let's consider this a little bit more carefully. So I use PyTorch as a framework. So here you see some imports like import torch and torch nn like nn as nn and torch nn functional as f, and some sort of summary to get summary about our neural network. We create these sort of networks in PyTorch in form of classes that inherit from the NN module. Here I have a constructor that takes input shape. This input shape will define me how large is the image that I am expecting at the input and the number of classes. So this neural network is even a bit more allows us to solve a bit more broader set of problems than just recognizing digits. So you can have more classes, you can have larger images or smaller images. So depending on what you want, you can even change these parameters and get something out of it. Good, so we initialize the parent class, and we are starting create our layers inside. So the first layer is the convolutional layer. So I'm creating the simplest possible network. It's not even LeNet, it's even simpler. So we make some convolution. In this convolution, I have one input channel. So I have a grayscale image that I get as an input, and I have 6 output channels defined by these variables. So out channels is 6. This means that I have 6 different kernels performing convolution at this layer. I set the size of the kernel to 3 most commonly used. Padding and stride is just how far you jump with your kernel when moving through the image. So nothing special. The next layer, average pool 2D layer. We have almost considered that, because when I told you about the max pooling layer, you can guess that the same thing is average pooling layer. So I have an image, I split it into some parts 2 by 2, so it's performed by setting kernel size 2 and stride 2, and then in each of these blocks I take some average value of whatever is there. So I add all the numbers, I divide them by 4. Here I have a layer that just changes the shape of the data, so nothing actual is performed here, so just data is reinterpreted as a vector instead of a 2D image. And here I make a fully connected layer, so here you see the NN linear that we saw before, and it is performing that's a fully connected layer that takes everything that we have from the output there and generates some number of classes that we have provided here. It would be something like 10, so all the digits 0, 1, 2, 3 and up to 9, and that will provide us the final result. After creating this on constructor, I need to define a function forward. So function forward defines how do I calculate the output basing on the input data. So here you see x, that will be the input data. As an input data I expect image 8 by 8. So what do? I perform convolution, so here it is, convolution, I perform that on x, I get result of that convolution. I perform activation function in form of hyperbolic tangent. So here it is, I perform torch tangent on the result of the convolution. So this variable contains a result of the convolution with activation function. Now I perform average pooling from whatever I have here after the convolution. I perform that pooling, I get some new numbers. This is some smaller image with 6 channels, I guess. Here I just change the shape, so nothing actually was done. And here I perform the fully connected layer on that flattened array of numbers, and an activation and I use softmax to get results in a range from 0 to 1. And that will be my out result. This function should return only out result let's say, in almost all cases. Here you see I'm returning a little bit more like result from each layer, but that's performed only for us, only for a demonstration. I will show you a little bit later a demo when we will consider what is happening on each of these layers, and you can see that more clearly. So actually, if you are just doing a neural network, don't do this, don't return each layer, just return the output that you need. But in case you are making some sort of demo, well, that may be pretty helpful. Okay, what do I do now? Here I create a model, so model of my RandNet, so some sort of random network I have created. As an input shape, I use the shape of my trained data. So from the trained data I take one image and I ask a shape of that image and I use that, and I tell that I need 10 outputs that will correspond to all the digits from 0 up to 9. And here I just ask to write some sort of summary on the model, so I can check that whatever I have created more or less corresponds to whatever I expect to have. And here you see different layers listed and their shapes. So convolution layer takes an image and returns 6 channels with 8 by 8 images. Average pooling does not change the number of channels, but makes all images 4 by 4. So I have split them into that sort of blocks, calculated averages, and now they are twice smaller. Flatten does basically nothing, just transform them into a one long vector, so you can multiply 6 by 4 and by 4 and you should get 96, so the same number of parameters. And here is fully connected layer. It has 10 outputs, it takes 96 inputs and has 10 outputs. So all 96 inputs are considered by each of the 10 neurons that you have there, and then it generates some number. And this number then goes through softmax to get us something from 0 to 1. Here is the function softmax. These are the outputs. You see that we take the exponent of the number that we get out of the neural network divided by the sum of all exponents that we were able to calculate, so all the outputs. What does it mean? Well, whenever you have a very large negative value, this exponent will be close to 0, so you get something close to 0. Whenever you have some large value, well, depending on what you get from the different neurons, you make this normalization and you may get something either close to 1 or some smaller number. So whatever you get is in the range from 0 to 1, and thanks to this normalization they all add up to 1. So you can reinterpret them as probabilities of getting certain digit. Now we need to train this network. So we have created a network. But the best I can do now, just set some random values into that network and get some random result. Let's make this result a little bit less random. I need somehow to estimate that my neural network works correct. So I define a loss function. As the loss function, I use so-called cross-entropy loss. It is already defined for me with the PyTorch, so I just reuse the function that it has. In practical cases, you will probably need to write your own loss function depending on what is your problem and what do you consider in the context of that problem to be good or bad result. So here it is. What it actually does, here you see the formula. It takes the logarithms of the outputs. These outputs were generated with softmax, so it takes logarithms. It multiplies them by ti, which are the truth values, and sums everything up with a minus sign. Nothing very complicated. So basically, if your output was a large positive value and the truth value, these truth values, they are 0 or 1, which means that this exact image was corresponding to that ith class. So when I have image, let's say of digit 2, I will have t2 equals to 1, while all the rest t's will be 0. So they zero out everything else, and we consider only the part that was returned with the z with index 2. And if this z was large positive, we get a large negative value that is considered good, because you remember that the lower the loss function, the better is the performance considered. When we get some large negative value, that means that all these sum will become positive and we will get large loss, and we will consider that as a poor performance. So that's what we have. We need an optimizer, so a method, an iterative method that will iteratively make our neural network better and better and better. I use ADAM. You can find that in a list of methods that I showed you earlier. So here here are these methods. Here you see ADAM, discovered 2014, and you can see it even here in this picture, just in case of very simple functions. So here it is, the red one, I guess. Good. So I use ADAM as my optimizer, and basically with this I have everything I need. Now I want to perform 4,000 epochs. I set my model in the mode train, and for each epoch, what I do, I set 0 grad to the optimizer, I put my training data through the model, so I get the outputs. Now I use these outputs and the ground truths that I have, so that ground truth defines me these TIs in the cross entropy loss. So I send them to the cross entropy loss and I get my loss, so I get some, basically some number that tells me how good is my neural network. Then I perform a backward propagation. So this is a little bit, let's say, more complicated object than just a number from the engineering point of view, because it is connected to the neural network in a sense that you can call function backward and it will calculate certain gradients and send them into the neural network and force it to update the parameters. So here they are performed. Then you perform a step on an optimizer. So, and then we can get with loss item, we can get epoch loss as the number. And once in 500 epochs, I will print that number out so that we can look whether our loss is going down or not. So whether our neural network is training or not. So let me start it and let's look what happens. So here we have loss 2.3. Let's wait a little bit more. Here we have 1.6, so loss is diminishing, which means that our neural network is training right now and we are getting some results. 1.5. Now our change in loss is getting smaller and smaller, as you see, so we have probably mostly trained our neural network, and this is just some sort of small fine-tuning, and probably we'll be not able to get much of it with this much of training. So probably I had to stop it a little bit earlier, but I don't think that really matters so much. So here we have 1.47 and just in a moment the training process will be complete. Here it is. So we can check our neural network whether it works or not. So here you see I switch my model into the evaluation mode, and I will try to perform evaluation of this model on the on different data sets. So here I am evaluating my model on the test data set. So I have trained it on the trained data set. Now I'm evaluating that on a test data set on the numbers that it hasn't already seen. Here you see I get some outputs. I use these outputs once again for the in the loss function that I had here, the cross entropy loss, and I calculate the overall loss so that I can see how large it is on the test set. So I saw that on the training set, I want to see that on the test set. Here I have some sort of predictions and I calculate the number of correct predictions depending on the class, and I organize this prediction in a thing called confusion matrix. So here you see that confusion matrix, that's true label versus the predicted label, and here you see the number of correctly predicted classes and the number of missed classes, and we can even see which classes were mixed up. So for example, at some point 1 and 8 were mixed up, so probably took out 8 for 1 or 1 for 8, so whatever. And here you see all these results, and the perfect matrix of course should be diagonal. So here we see the larger numbers are on the diagonal, so probably this is a pretty good neural network able to recognize something and get us some results. Let's look inside this neural network. So here is some glimpse inside into that layers so that we can appreciate what happens there. Here you see the input image. Here is 4. The next layer is the convolution layer. So we are performing convolution. But you remember that I have defined 6 different channels in the output. So I am performing basically 6 different convolutions. and each convolution gives me a little bit different picture. So here you see them all. So 1, 2, 3, 4, 5, 6. So all 6 results are in this column. Then we perform average pooling. So here you see results of average pooling. So I have taken all these each of these images, and I have basically split it into blocks 2 by 2 and calculated average value for each of that blocks. So here they are. Then all this data is sent to the fully connected layer and then to the softmax. Result of the fully connected and then softmax you can see on the right. So it has certainly defined that this is digit 4. Let's look something else. So here is 7. Once again, we see that our neural network is pretty definite. It tells us this should be 7. And here you see how that 7 proceeds through different layers. Let's check some more and more and more. So here you see. Okay, let's do one more test. That's probably the last test for today. Let's try testing our neural network in some more real-life conditions. So that were the images that were pre-processed somehow. So people draw all these digits, and then they were transformed into a digital form, and so on and so forth. But let's try to do that by hand. So suppose I am drawing some digit. I'll try to draw it in here. Okay. So I draw something. Here I have that cropped out, and here I have transformed this image transformed into grayscale 8 by 8. So now I'm trying to perform recognition, and you see that I get number 5. So that's pretty close to the to whatever I have drawn here. So let's try something else. So let me draw, for example, number 2. I perform recognition, well, and I get wrong result. That's pretty possible. Let's draw number 8. And we get number 8. So you can see that this neural network, despite being incredibly simple, so it has just like 3 layers and nothing more, is already capable of recognizing certain symbols, let's say digits from 0 to 9, and getting some results. So maybe it can be even useful in certain contexts. So that's what we basically have. And with that being said, I guess we can wrap up our lecture. So let's just some final time reiterate what we have learned, and that will be it. So first of all, we started with the general idea that you can look at a neural network from the 2 different standpoints. So one is a standpoint of an engineer. So you can consider that as a program with certain internal parameters. These parameters, you can tune them up with the special algorithm that you call a training algorithm, or you can view it from a standpoint of a mathematician, and you can say that basically creating a neural network, so creating some architecture, I am choosing a family of functions. This family of functions is indexed by the internal parameter of that parameters of that architecture, and the process of training is the search for the best function we can get. The best function is defined, the idea of the best function, what we consider good or not, is defined separately with the loss function. We have defined this loss function in our example as a cross entropy loss. It takes the output of the neural network, maybe some ground truth data, so depending on the problem, you may have them, you may not have them, but most cases you do, because you do have some data set. It takes this data and it calculates you a number. The smaller this number, the better your neural network performed. And we have some algorithm that is capable of tuning that internal parameters of the neural network and basically finding the best function of that family of functions by performing certain iterations, and at each iteration making our result better and better, so making our loss function smaller and smaller. In our example, I used ADEM, and you saw that there are many different other methods that you can use in the PyTorch or different frameworks, and they all are based on the calculation of the gradient, because these are first order methods, so they calculate gradient, and they may add something to that gradient. So in most cases these are some sort of momenta or something like that, so they have some memory of whatever happened on the previous steps, and at the end of the day you get to the best best set of parameters for your neural network, and thus best function that performs whatever you want. So with that being said, let's wrap up and up to the next lecture.